great day in the magic world of soap films. A unique exhibition. We present the most spectacular soap films in the universe. Our main attraction, Plato's Magic Surface. The greatest attraction between...
Hello, organ grinder. I'm Kalle. This is what to this fancy exhibition?
Yes, straight ahead, just past the guard.
Hey, Kalle, you're too young. It's too dangerous alone in this palace.
It's okay, mister. I'll be careful.
New visitor, stop. Kalle, stop. No fee paid, stop.
Wow, funny machine.
Ladies and gentlemen, welcome to the first exhibition of Plato's Magic Surface. I'm James, the computer, and I'll guide you through our palace. You have all played once with soap bubbles, and you know the iridescent colors of soap films. For 200 years, these surfaces have been among the best studied objects in mathematics. They occur in chemistry and crystallography as separating surfaces between grids of atoms, and they are used in architecture as models for light roof constructions. I will guide you to a world of these
Surface.
Already crashed? Escape button. Now let's see.
Let us go back to the origins of these surfaces. Back to the middle of the 18th century. There, the French mathematician Lagrange asked the famous question which started everything. How does a surface with smallest surface area look when it has a given curve as its boundary? Soap films solve this problem immediately, as we will see, but mathematicians tore their hair out. Here, in this temple, we have the very first examples mathematicians were able to describe. the cooling tower-like catenoid and the stair-like helicoid from the middle of the 18th century, which deform here one into the other. But no further surfaces were discovered then. So, for simulation, in 1816, a prize was set out for the discovery of a specific surface lying in a cube. Hans Ferdinand Schack failed with the problem, the so-called jargon problem. But he discovered many surfaces which came close, and people were so impressed he was awarded the prize. Another 30 years had to pass before Hermann Amandus Schwarz found the real solution to the Gorgon problem using completely new mathematical techniques. Today, we can selectively construct many soap films and modify known surfaces into other shapes. Extremely interesting is a look in the works of the old masters. Lagrange, the forefather of soap films, suggested around 1760 investigating these surfaces mathematically because they have the smallest surface area. Also, Hermann Amandus Schwarz did pioneering work. For him, visualization of new surfaces was already indispensable 100 years ago. His most famous surfaces, like the soap film in a spatial quadrilateral, were visualized as a copper plate engraving and printed in his papers. Today we are astounded by the technical and aesthetical perfection of his pictures. To Schwarz's most spectacular successes belongs the solution of the jargon problem, which he cites at the beginning of his paper. Is it possible to bisect a cube in such a way that the intersection surface is bounded by the inverse diagonals of two opposite faces of the cube, and that the intersection has minimal area? The surface in the upper picture, obviously, is the solution. Schwarz was a master in the application of the theory of complex numbers to minimal surface problems, and he succeeded in discovering numerous breakthroughs. I will guide you now to the centerpiece of our exhibition. A wonderwork of technique unique in space and time. The professor created the universal soap film, Plateau's magic surface.
Oh.
This surface can take on the shape of every soap film existing on Earth. As soon as the boundary curve changes, the surface changes magically to the correct soap film, and every soap film out of all surfaces on any boundary curve has the minimal surface area. The magic plateau surface consists of a unique material. It is elastic like a soap film and filmy thin. It can even simulate unstable soap films which would burst immediately in nature.
Oh.
But it is very sensitive. Nobody should come close to it. Kalle! Attention!
Ah!
You naughty rascal!
My dear little friend, it is unbelievable. That's a fine mess you've made. Just a few minutes in our palace and you've already exterminated our centerpiece, destroyed into thousands of fragments. Do you know how much time and ingenuity I put into that surface?
No, I can't imagine. But I feel very sorry for having done that, Mr. Professor. I didn't mean to do it, and I promise I'll never do it again.
My surface was unique on Earth. It could simulate even unstable soap films, which do not exist in nature. Everywhere it was forbidden to touch the surface.
But I still can't read. I'm very sorry, and I couldn't know the thing is so sensitive. I have never seen such a piece before.
Okay, little boy. Your name is Kalle, as James told me, yes? Well, Kalle, you're still so young, and I will forgive you this once. With some work, we can get the thing fixed.
Then I won't be punished? And you can cure the surface? Wow, that's great! How can you do that? Do you need to know many formulas for this?
Yes, one needs to know a number of things about soap films, but it's not all that difficult. I will explain why that surface was so worthful and lead you around the palace.
Whoops! What was that?
Our soap film machine. Before we invented the magic surface, we needed to study new shapes to experiment. It takes a metal wire from the stack and dips it into the soap solution. This contour is similar to the catenoid.
What's that?
Instant freezing. With that, we also get unstable soap films which would burst immediately in nature. But I can explain that better on the wall over here. You should imagine such surfaces as elastic skins of rubber which try to contract themselves. Watch the ball on the right. The ball always rolls into a valley where it has less energy than before. In a state of rest,
It has locally minimal energy. It's similar with soap films. The surface tension causes the soap film to contract and to go into a state with minimal surface tension.
You mean with minimal surface area?
Yes, of course. For soap films, energy means the same as surface area. The rubber band is like a one-dimensional analog of a soap film. The mutual attraction of the rubber molecules causes the band to jump back in its previous position with minimal length. Similar to the rubber band being fixed between 2 points, the soap film is fixed in a wire curve. If we now disturb the soap film, it immediately jumps back to its original position.
There's only one soap film in a wire?
No, usually not. Come along with me and have a look at the laboratory table. Here we see two identical metal wires, but with different soap films. There. Well, compared to the ball we saw before, it could stop in different valleys. It needs big changes for these surfaces to decrease their surface area. But it gets even more mysterious. Between these two rings, there exists no soap film, which is spanned in both rings simultaneously. However, if both rings come closer, a cylindrical soap film can form. And the most astonishing is that there exists a further unstable soap film.
Surely you must have very complicated formulas, right?
I hate to disillusion you, but the world isn't so simple that one knows a formula for every object. One can use, however, maps similar to the ones used for the description of the Earth.
How else can you describe soap films?
Come along. I'll show you a new surface.
Wow, very pretty.
The surface here is generated with a computer. For that, we use the property that soap films try to minimize their surface area. This can be used as description to generate them with a computer. My program is called Grape. I'll show you how I compute the surface we just saw on the wall. First, you know that a computer cannot keep all the points of a soap film in its head, of course, so we approximate the surface with the help of triangles. So now we have the initial surface of triangles in a given boundary curve. I'm already using some bigger building blocks. That makes life easier. We merge the building blocks to a single triangulation and, okay, let's go. The computer now decreases the surface area. Look, you see how the surface already resembles a soap film in the boundary curve. We have a problem with the big triangles in the middle. Here I must refine so that we can compute more exactly.
But the surface still is not completely smooth.
Well, we can only compute an approximate solution. And you see, in the middle, it's already quite smooth. now, we need to further transform the surface. And there. They deform into each other. We have a basic block of the surface we're looking for. Now, reflection. With this, we extend the basic piece to a bigger surface. Only then do we see the surface in the picture. But it's still not so attractive. That's what I do after work, make them beautiful.
I want to see more of the palace.
But you must behave, you promise?
Sure, of course. Where do we go first?
At first we'll go to ends of noise.
What's that?
Good question. The soap films you see in there all arise through the deformation of the catenoid. That's this cooling tower-like surface. Ah, yes. At first, the helicoid. That's absolutely the simplest soap film. You see, it's like a winding surface, since it arises through winding a plane.
Is it always a soap film during the winding?
Yes, they are. In other words, they're a family of soap films. The starting plane deforms continuously into winding surfaces.
Ah, a winding slide. And a winding stairs. Is it possible to extend the surface at top and bottom? Should work, shouldn't it?
Sure. That works for the helicoid, but in general, it's mostly impossible to enlarge the boundary. So, now we have the catenoid. Watch out, Kalle. Now we're going to do an exciting experiment and try to build a tunnel into the catenoid.
May you do that? Is that allowed?
Now keep cool, Kalle. We build in 2 new rings and move both further inside. As we move further inside, the more the other parts of the surface drift away. And if we try harder... Oops.
I could have told you that before, that it doesn't work.
Well, it's not as simple as you think. Look now, there is an incredible wealth of other variations which do work. Though we failed building a tunnel through the inside of the catenoid, we can pull new tunnels to the outside. In an arbitrary direction. And one could even pull one to infinity.
Wow!
catenoid with 4 trumpets is much flatter in the middle, and therefore it's more stable. You see, there we can build in a new connecting tunnel. Building tunnels, by the way, is a very new technique.
And I can make that surface all by myself just by dipping 6 rings into soap?
It's not that easy any longer. The surfaces are unstable in nature and would instantaneously burst. Let's just go into the periodic room. There's an astonishing surface there which periodically continues to infinity in every direction. Do you recognize the surface? The extract in the wire is Jargon's surface from the temple.
That's right, but how did it become this big checkerboard surface?
But that's an astonishing property of soap films. Whenever the boundary consists of a straight line somewhere, then one can rotate a copy of the surface around the line. Watch what happens. You see? The new pieces fit exactly after the 180-degree rotations.
Super! Just gone to become gigantically huge.
Slow down now. There still comes something but different than what you expect. Namely, one can also reflect the surfaces. If the soap film contains a symmetry line, we can always extend the surface by reflection.
Wow, like in a hall of mirrors.
That's right. Now I'll show you my very hottest research. We need to pass by the cyber room to the Hall of History.
Cyberspace? Can I fly in there?
No way. That's far too dangerous. You're much too small. And anyway, the cyber room is closed today. Now we go to the very nice Hall of History. This is my collection. The most famous minimal surfaces of the last 200 years. Pay attention, Kalle, and don't touch. You're already familiar with the first two. And another well-known surface by Shaq. Then the Eniper surface.
Fancy.
Do you recognize this? Schwarz's copper plate engraving again. Riemann's surface is like two catenoids slightly displaced, stapled over each other. Schön discovered many surfaces used in crystallography. Chen and Gachstetter built a handle into the Eniper surface.
Fantastic.
And the most celebrated surface of modern time, discovered with a computer. A typical handle. It's unbelievable, but true. A handle built into a helicord. Yes, and here, this is my surface. I'm still not completely ready with it. So you see, yesterday I had an ingenious idea. When I exercised with soap bubble soup, they formed such an interesting shape with a quadruple symmetry, and if I would succeed in... Exactly. Only one has to move the boundary further to infinity, then implement a connection from top to bottom. Yes, exactly. And then turning the surface by 180 degrees. Hold on, doesn't that contradict? But when the connection is from top to bottom...
Flight, flying slowly.
Whoops, how do I steer?
Attention, entering hyperbolic space.
Wow, where am I now?
Leaving hyperbolic space. excessive speed, attention, instability.
Kalle! Goodbye, Kalle!
Ciao, Professor!
Bye-bye, Kalle!
Ciao!
Come in, come in! Come in, one and all!